Bismillahirrahmanirrahim. Dear student, Assalamu alaikum. Yesterday I gave a extensive expression of the mathematics, and I am sure you have gotten the idea. You will be thinking about that why this is too much mathematics. It is the reality that we should have some awareness about the basic concepts of the regression, and that are proved only by the mathematics. So I would not like to repeat that exercise of the previous day, but I will suggest that you should not confine yourself only to these basic formulas. For example, I gave the formulas of beta 1 hat and beta 2 hat. You should go for the other books and you should search for other formulas, and you should remember this, because in the final examination or in the midterm you will be asked to solve some of the formulas, or you may be given the values and you may be asked to find the values of the beta 1 hat and the beta 2 hat, that are the slope and that are the intercept and the slope coefficients. After this we started, and now I assume that you have geared up your line and you have started, you are burning the midnight oil to capture the ideas. I am just concentrating on the basics ideas, and as you will be aware of this, I am sure you will be able to run fast with me. So what we completed yesterday, that let it not be repeat here, and I would just like to start from today, that what we are going to cover today, and today we are covering a lot of areas. The first one is the assumption of classical linear regression model. As you know, yesterday we started this topic, and if my memory, I can trust my memory, I think we completed up to 3 or 4 basic assumption of the classical linear regression model. After this, we will be talking about the covariance of the parameters, that are beta 1 hat and beta 2 hat. Then we will be talking about the standard error or precision of the estimate, because when there are repeated sampling and everyone will come with the different values of the beta 1 hat and beta 2 hat depending upon his sample, definitely we should have to choose that which is more near to the true parameters. After this, a very interesting theorem, the Gauss-Markov theorem, that will tell us that what are the basic properties and the characteristics of the ordinary least square estimates, that are the beta 1 and the beta 2. And if time will permit, we will discuss coefficient of determination, that will tell us that our model is how much fit, or you can say that this is the goodness of the fit, or you can say that the how much variation of the dependent variable in which we are interested is explained by the independent variable that we have included into our model. So I would like to start formally from here, that what the assumption of the classical linear regression model, a bit 1 minute discussion on this, that every social sciences and every, you can say, theorem needs some of the basic assumption. We will be talking about this, that whether these assumptions are real, and if these are not real, what is then the purpose of explaining and stating these assumptions. So what this means, you should remember this, that if these assumptions are fulfilled, definitely our theory becomes true. And if someone or all of the assumptions are lapsed, then there is problem. And in our later discussion, we will be covering that what problem arises when any of the fundamental assumption is lapsed. So these will be called, we will call them that these are the problem in the estimation. So starting from the first, I will not give the detail, but I would like to just state that the model is linear in parameters. Although there are models that are non-linear in parameters, but they have some different techniques to estimate the non-linear parameters. But as we are concerned with the ordinary least square method, so we are taking the assumption that our model is linear in the parameter. I will again say that we have nothing to do with the variable, that whether the independent variable are linear or non-linear, but we will just concentrate and ensure that our model is linear in parameter. And interestingly, you know that what is the meaning of the linearity, that the power or the index of the parameter should not be other than 1. It should be only 1 and 1. So this was the first assumption of the classical linear regression model, that we assume that the model should be linear in the parameter. The second assumption that I explained yesterday, that x values are fixed in repeated sampling. If I would like to give again here some of the brief structure here, if you remember, this was the x, this is the y, and if you look at here, this is the x. So here we fixed the x, and there were many values of y. Here was, this was x2, you can say there was value of this. So what we said, that here against one value of, there are many values of the y. So what we do in sampling, what we want, that we want against each value of x, there should be only one value of y. So it is one-to-one combination. So what we will be doing in repeated sampling, we will be ensuring that the independent variable are fixed, and we are taking the values of we are taking one value out of this. More technically, x is assumed to be non-stochastic. Non-stochastic means non-random, that although you should note that I am giving the footnote that although there are the conditions when even independent variable becomes random, but that is intensive technique. Here we are supposing that we are fixing the values of the independent variable in repeated sampling. The third assumption was that the zero mean value of the disturbance. As you know, that disturbance captures and it includes all the forces that are outside the model, and they have ability to affect our dependent variable. So what we say, that although we can't capture these forces, but we can make assumption against the about these forces, that they affect our dependent variable randomly. Randomly means their plus minus is cancelled out, and they can neither inflate our dependent variable, or they can deflate, or you can say suppress our dependent variable. If I would like to write this in mathematical notation, it becomes expected value of ui given xi, ui given xi is equal to 0. That at each value of x, the disturbance sum should be equal to 0. If I would like to run through this because I explained it yesterday. Look at here, if this is the regression line, and if I say at point here, the plus u's and the minus u's should be equal, and similarly at each point, plus u and minus u should be equal, should cancel out, and their sum should be equal to 0. Now I am going towards the fourth assumption that we were discussing yesterday when the curtain fell. Homoscedasticity, very, very important assumption of the classical linear regression model. What this is, homo means equal and scedasticity means spread. It shows it is about the error term, that at each x value, xi, x1, x2 and x3, that on each x value, that the variance of the error term should be a constant number. It should be any constant number, but if it is 100 against x1, it should be 100 against x2 and all the x's here. So I would like to explain it here as I find space at this slide. So what is this homoscedasticity assumption? This is, I would like to go to the next slide. So this is what is, I would like to show in 3 digits this is 1, and this is function of u. Now we are plotting the u, this is the y, and this is now the x. If at each point of x, for example, now this x connects here, and if we have the equal spread here, and similarly if I call this is the x2, this is the x1, this is the x2, and there is the similar spread of this, and this is the x3, and the spread is almost the same. You should not confuse that due to raw hand and the electric pen, the grip is not as clear as should be on the other pen. But I can see that I have made that the spread of the error term against each value of the xi that we have fixed, it is homogeneous. It is homogeneous. What this means that at each point there should be the variance of the error term should be constant. You can write this, that expected value of ui square given xi, it should be a constant number. It should be a sigma square, that is the variance of the error term, and it should be a constant. What this means that against x1 there will be sigma square 1, it should be equal to sigma square 2, and it should be equal to sigma square 3, and so on. It should be equal to sigma square n. So what this means, I may think that the confusion may arise that I am supposing that it is only a one number. It could be any number, but if we take 100, then it should be 100 on against all the x's. If we take 50, it should be 50. So it means that every place against every fixed value of the x, the variance of the error term should be a constant. I think it will become more clear if I draw a heteroscedasticity diagram, so that when you will make compare of this, you will come to know that the concept of this homoscedasticity will become more clear. Similarly, repeating this diagram, so what this says, this is f of u, this is y, and this is, you can say this is the x, this is rather than x, this is x. And if I take this value, look at, I am deliberately making that the spread is of this kind, but at this time you can say that I am deliberately making a huge spread, and if this situation continues, I can further make such kind of things. So this is the example of heteroscedasticity. Hetero means different, heteroscedasticity. So this is homoscedasticity. Homoscedasticity equal spread, but heteroscedasticity mean different set, or you can say the varying spread. So what this is here, so now what, how the this will, we can write it ui square over xi is equal to sigma square I. Now this I means that the variance of the error term is changing, is varying with the as the xi varies. So this was the concept of homoscedasticity and heteroscedasticity. Now immediate question that in your mind may arise, that what if there is no homoscedasticity and what if there is heteroscedasticity? This question will be answered at a later stage, because when there is heteroscedasticity, our estimator that are beta 1 and beta 2 heart do not perform well, and we will be talking about that what happens if this heteroscedasticity enter into the model, and what are, fortunately we have the remedial measure and we have as well as the detection method. So you should not worry about that. If these concepts enter into the model, we are unable, or you cannot say that we are helpless and helpless. There are number of ways to remove this and to detect this. Then assumption number 4 is no autocorrelation between the disturbance. This is again very interesting. As we said that the disturbance captures those forces that are out of control of the researchers. So what is happening? These are affecting our dependent variable randomly. So, but unfortunately, if any of the two disturbance terms, say ui and uj, they are correlated with each other, then there is a systematic trend that can affect our dependent variable in a systematic way. So first I would like that what this means in notation. If you look at here at this point, what is this? That the expected value of ui given ui, no autocorrelation between ui, uj. ui, uj is equal to 0. So I would like, as here is a bit confusing, I would like to write it expected value of ui, uj is equal to 0. What this means that there are many error terms ui, u1, u2, u3 up to un. What we are saying, what we are taking the assumption that these error terms should not be correlated with each other. Because if there is a systematic trend that shows that our residual terms are showing a systematic process, it means that these residual terms are affecting our dependent variable in a systematic way. So what this means, I would like to show here that what this means. For example, this is a yi is equal to beta 1 hat plus beta 2 x plus ui, and if this is now a random variable and it is affecting y, this is. So if it is random, its effect on the y is random. You can write it as also the expected value of y over x. Do not confuse yourself at this stage. So what this, if this ui is linked with previous uj, so what this means, now there is a link between ui, this is uj, and this is linked from here to here, and this is now affecting this variable. So it can shows now what I am going to say, what is the meaning of this discussion, that the effect has become non-random. It has a systematic effect, and as our assumption about the error term is that it has a random effect, as this lapses, we may suffer, and we can say that our coefficients, that are the intercept and slope coefficient, they may face some of the problem. So I would like to give you an example that what is the meaning of the random error term and what is the meaning of if they show any systematic trend. So take this example. First I will be showing that the error terms are positively correlated. If I plot, this is the u plus, this is u minus, this is u plus, and this is u minus. If these are positively correlated, what this means, ui relationship is going in this way. This relationship is going in this way. So what this shows, that now the error terms are showing a systematic trend. They are not random. This is the randomness. We need randomness because we want to make their effect on the dependent variable random, that will become 0. So if you look at this, this is a positively slope, and what this means, the next coming error term is positively related with the previous one. So it is showing a systematic trend, and if now they have a systematic trend, they have ability to influence our dependent variable in a non-random way. So there may be a problem. So I again say, if these terms are correlated, if these are negatively correlated. So what this is, ui, this is ui positive, this is ui negative, this is ui positive, and this is ui. This is only a you can say that this is, we have bifurcated into 4 parts, and you know where the plus and where the minuses are. If it gives such kind of trend, these are UIs, many UIs, you can say 1 million UIs. If this is the trend of the UIs, this is very dangerous. It shows that the error terms are negatively correlated. The next term is negatively correlated from the previous. So negatively or positively doesn't matter, but the matter is that there is a systematic trend. We want random. We don't want any of the trend. So when there is systematic trend, definitely the effect on the dependent variable, that is the y, will definitely be non-random and systematic. Now I would like to show that what is the randomness of the what we want and what we make the assumption. Look at here, these are the UI that are the positive, these are UI negative, these are UI pluses, and these are UIs minus. What we want, if you look at here, now you can't make any of the assumption, you cannot deduce any of the inference that whether there is a positive relationship between the residual term or negative relationship. No relationship exists, and this circle of this dotted line shows that the effect of the random term is on the dependent variable is random. So our required assumption that we talked about is that this is that there is no autocorrelation between of the error term. So this was positive negative autocorrelation, and this was the positive autocorrelation. What is our sixth assumption? So sixth assumption is zero covariance between UI and XI. So we talked about up to here, and this was as I wrote here. Do not confuse that if I write only UI uj equal to 0, it is similar that expected value of UI given xi and its result with UI uj given xj is equal to 0. These both terms are the same, only the notation is different, so confusion should be avoided. What is our sixth assumption? Now you will be thinking that how many assumptions we are going to complete. There are 10 assumptions about the classical linear regression model. So this is the sixth assumption, and what this is that the zero covariation between UI and XI. This is a new assumption. As in the beginning I told that here, if you see, just let me give that y is equal to function of x as it is function of betas. So it means, and plus this is function of error term. So what this means, if we want to see the behavior of the y, I would like to write it in a simple way. Y is equal to beta 1 plus beta 2 x plus ui. This is xi and this is ui. So as I said that if we are interested in measuring the behavior of y, it depends on xi and ui. So if we will know about that what is the xi and what is the ui, then we will be able to predicting in a better way that what is the yi. So we are making assumption about the xi, that how the x variable are generated, and we are talking about that how the ui are generated. So the sixth assumption here is that there is zero covariance between ui and xi. What this means, xi, the independent variable, and the error term has no correlation. They are not moving in a systematic way. They are random with each other. So what this, I would like to have explain it here. What this means, that look at this, our model. The model is y is equal to beta 1 plus beta 2 x plus u. Suppose that our ui and xi are correlated. Now immediately you can guess what is happening. First the xi effect will come here, UI effect, we are supposing that it is random, but if UI and XI correlated, it means now there is the emergence of the third factor. Rather than XI and UI, now XI and UI are correlated, and then the effect goes on Y. So what is this? UI affects, I can write here that UI affects XI and that affects YI. So what we suppose that there is, if I would like to write it in a notation, expected value of UI XI 0, this is covariance. Covariation of UI and XI. This is again very simple, very interesting and very important assumption. What this assumption says that the independent variable has no link with the error term because their effect should be independent, and if they are correlated, now one is affecting the other and ultimately the independent variable will be affecting the error term. What is our seventh assumption? The number of observation in n, that is the n here, the number of observation in a sample, this is the n, must be greater than the number of parameters. So if I would like to write it that n should be greater than, you can say, the number of parameter, that is the p. So what this says, if I would like to have this, interestingly, if x and y, we can measure the coefficient from 7, 8. 7, 8 means that this is one pair. So to estimate one parameter, I am repeating again, to estimate one parameter we required one pair of this kind. For example, if there is only one pair and I am interested and I am, you can say, over efficient to measure two parameters from these values. What this means, I want to run the regression of such kind that y is equal to beta 1 plus beta 2 x. Now you can say there are two parameters, beta 1 and beta 2. If I want to run this regression, it means I am interested in two parameters, beta 1 and beta 2. And on the other hand, if there is only one pair of, if you run this regression, you will find such kind of message from any of the statistical software, and we will be doing it on the eViews. I may start it within the next 2 or 3 lectures, that there will be message insufficient number of observation. So what this means, that the number of observation should be greater than the number of parameters that we are wanted to estimate. So this is another assumption, very simple assumption, very easy to comprehend, that if we are interested in estimating the 5 parameters, we need at least more than 5 observations. The 8th assumption, the x values in a given sample must not all be the same. This is very, very important and interesting. Look at here. If this is the y, you have the value of y. This is, for example, 3, 4, 8, 9. And you have the x value only 1, 10, 10, 10 and 10. So what will happen, that here xi will become equal to x bar, mean. Then there will be no difference between the mean value and the xi value. When this situation occurs, we are unable to estimate many of the parameters. So we are assuming at this stage that the x values in a given sample must not all be the same. There should be variation, and at later stage I will be explaining the more variation into your independent variable, it is more good for your analysis. Because if there is no variation, then what you are going to measure the variation in y. For example, if you want to measure, I would like to again say that you are interested in consumption and this is the income. If the families have income of 100, 110, 105, 107. So there is very small variation on the income side. So if you are measuring this and you will measure very small variation of consumption. So what this means, the first is कि आपके जो x's हैं वो same value नहीं होनी चाहिए. And on the basis of this, I am going one step further. The more variation captures your independent variable, the more reliable results. What this means, it will explain more proportion, more variation in the dependent variable, that is the y. So if I technically would like to say, this means that the variance x must be a finite positive number. For example, if there is no variation, the variance will become 0. If all the x's are same, the variance will become 0. So what we say, that the variance of x mean here x1, x2, many x's as you include into the model, they must be some positive finite number. So what is the ninth assumption? We are now going to conclude our discussion about the assumption of the classical linear regression model. The regression model is correctly specified. We are assuming in the beginning that our model has no specification bias. What this means, we have captured the relationship in a proper way. That if there was the nonlinear relationship between the variable, we use the nonlinear regression. Not in the parameter, but in the variable, because you know we are interested only the model that are linear in the parameter. So what this the ninth assumption is saying, that our model simply it is not the modeling of the you can say the dresses. This is model here means it is y is equal to beta 1 plus beta 2 x. What this means? We have fitted here the linear model. So what this means, this assumption means that we are presuming as priori we are saying that our model is correctly specified. The last assumption of this is there is no perfect multicollinearity. Perfect multicollinearity is that the x1 and x2, these are now two independent variable. There should be not a exact linear relationship. For example, if your x's are 3, 4, 6 and 7, and if I add only any figure, for example, if I say I add 4 to here, this will become 7. I will again add 4 here, 8, 10 and 11. Now this has become that x2 is equal to x1 plus 4. So this is a linear relationship, and this is called the perfect multicollinearity between the independent variable. We will be talking about this multicollinearity concept at later stage when we will be talking about the multiple regression analysis. Here we are confining ourselves to only two variable or bivariate regression model. So this was the 10th assumption, that there should be no multicollinearity, perfect multicollinearity. And if you see that if these are, if we take such kind of thing, if there is perfect multicollinearity, then there is a problem in the estimation. Now a worth million question. Now million not, I would like to say billion question. Are these assumptions realistic? Now we see that what the people say about these assumptions. The first is, some people argue that the reality does not matter because these assumptions are not real. These are not true in the real life. So what the people says who are in favor of these assumptions, what they say is, this is that reality doesn't matter. It is the prediction that matters, because you know that we are interested in predicting the expected value, we are interested in predicting the average value of the dependent variable on the basis of the independent variable. So now we are questioning our assumptions and we are synthesizing the different arguments from the people. So it is very interesting question that we see that whether these assumptions are realistic. The first argument we studied here is that the people say that for the time being ignore the reality, go for that what the prediction is. If on the assumption of these if on the basis of these assumption theory or the model is able to make a good prediction, then the reality of the assumption doesn't matter. The other people who are also in favor of this is the assumption help to build theory. As I said, that all the social sciences theories are based on the assumption of the sum of the assumption. So it is a fundamental, or you can say the starting point of any of the theory. So if these assumptions are fulfilled, you can say the model is a good fit, and you can say the model has the ability to predict the proper value of the dependent variable. The next is it makes the understanding simple. If without any assumption, as you say, I just wrote the model, but now we have simplified, because if we allow the all discussion, everyone to come into the model, that there is no delimitation of the hour that in which area we are going. So what we are going, that we are limiting our scope and we are just concentrating on our ultimate objective, that is the prediction of the dependent variable on the basis of the independent variable. So what this is, that if the people say, the scientists or whatever you can say, the people argue that the assumptions are necessary because it makes the understanding of the theory very simple. And the people who argue that the assumptions are not real, so we should not take assumption, they are being given answer that later we can check. What happens if these assumptions are not maintained? This is very interesting question, and our future discussion will be talking about in detail this, that people say first take the assumption, build up a theory, run the regression, draw a conclusion, and then see that what happens if 1, 2, 3, 4 are all the assumption are lapsed. So in the future discussion we will be talking that if our first assumption, second assumption, for example, I say if there is no homoscedasticity, or you can say if there is heteroscedasticity, then what will happen to our parameter? We will be talking about this. So people are in the favor that for the time being ignore the assumption, and at the end we can come back and check that what happens to this if we lapse any of the assumption. And I have discussed in detail that all the theories are based on some of the assumption. Researcher, this is very important, researcher must aware of these assumptions, because researcher is making the assumption about the error term or the independent variable. If he is not taking the making some of the assumption, he can justify it. It is not necessarily to take these 10 assumptions. If you have the ability and you think that these assumptions have no meaning in your research context, you can ignore any one of the assumption, but at the same time you should come up with a valid and concrete argument that why you are not following this assumption, and the people may suggest, may comment, may criticize that what is happening to your estimation if you are ignoring these of the assumption. So this was the stories about the assumption of the classical linear regression model, and now you can say the estimation of our OLS, ordinary least square estimates, is based on these assumptions. Now we will be talking about that what are the properties of the ordinary least square estimates. So we will keep on discussing this situation. So precision, the next is the precision or standard error of OL estimate. Now we are refining and refining our estimation, that we say that our estimated parameters are very near to our true parameters, that are the population parameter. I will be very sorry because I am alternately using the words parameters both for the sample and for the population, but you should remember that the estimates should be used for the sample and the parameters should be used for the population. So if I change it alternatively, you should ignore this. What is the precision or standard error of OL estimates? If you see the LSE means here, LSE, this means least square estimates are the function of the sample data. Every time your beta 1 and beta 2 change when your sample changes. For example, if A, B, C and D person comes with different sampling from the same population, their parameter will be different. Beta 1 and beta 2 they have different values of the beta 1 and beta 2. Now what we say that the estimate change, here you can see the estimate change as the data changes from sample to sample. This is interesting. Population remain the same, but every time we are drawing, for example, the random sampling, every time there will be different sample. For example, if there are 52 cards, if there are, I need not to suppose, out of a deck of playing card, Tash, I think you are aware of this, there are 52 playing cards. And if I draw, this is the population now, and if I draw 20 cards, this is the first sampling. If I draw then 20 other cards, this is another sampling. And if 20 people draw this, every time the sample changes. So as the sample changes, the estimates of the regression also change. So what this means, if 3 persons come before me and they say that this is my estimates beta 1 and beta 2, the other say the value of beta 1 and beta 2 as this, and the third one will come some new values of the beta 1. So who to choose, which is correct? So we need some measure of reliability or precision. So how we can decide that which person or which student has come with a good precision, or you can say that his model is fit. So the precision of estimate is measured by standard error. So this is a new concept, that we will measure the precision of the parameters, the estimates beta 1 hat and beta 2 hat with the standard error. There will be standard error formula. I am talking about the precision of the estimate, and how the precision of the estimate is captured. It is simply captured by the standard error. And now what is the standard error? If you see the definition here, it is nothing but the standard deviation. I am sure you are aware of this from your knowledge of central tendency and measure of dispersion, that what is the standard deviation. I will be just giving here some of the definition. What is the standard error? It is nothing but the standard deviation of the sample distribution of the estimator. And now immediate question comes that what is the sampling distribution of an estimator? Is simple probability distribution of the estimate. So need not to explain it further because you are aware of this. So what I am going to say here, that the standard error tells us that which parameter is better in comparison to the other parameter. Some of the formulas you should remember these formulas, because if you are unable to remember these formulas, you will be suffering at future stage, because you may be asked to find the values of some of the parameters. If you look at here, this is the variance of beta 2 hat, because we will be getting the standard, you know, the standard deviation is the square root of the variance. So if we are interested in the standard error, and in the previous slide and discussion I have said that standard error is simply the standard deviation. So it means we need standard deviation, and if we need standard deviation, first we find the variance. So what is the variance of beta 2 hat? Different variance of beta 2 hat different formula, and variance of beta 1 hat has different formula. If you look at here, this is the sigma square. This value is very interesting. This is the variance of the error term. This is the constant term, and this is the variance of the error term, and it is rarely known because we are unaware of this, and I will be talking about that. If it is rarely known to the researcher, then how we estimate this, I will be talking at later stage. So, and here if you see, this is the summation xi square. Here you can notice that the x is in small alphabet. So small x shows that it is equal to the deviation from the mean, x minus x bar. So if it is xi, it is xi minus x bar. So what this means, that the variance of beta 2 hat is equal to sigma square divided by summation small x square. So, and immediately now we can measure, if we measure the variance of beta 2 hat, we can immediately measure the standard error, and you know the standard error is simply the positive square root of the variance. Look at here, we have just taken the positive square root of the above formula, and this is equal to this one. And if you come to the variance of the beta 1 hat, it is a bit more complicated as compared to the formula of the beta 2 hat. So what is there? Here the two x's are being used. Here is capital Xi square. For example, this is xi, and if this is 3, 4, 6, and xi square mean, this will become 9, 16, and this will become 36. So this is xi square, and it is divided by the n number of observation and summation xi, and you know what is small xi, and it is multiplied by the constant variance of the error term. So immediately, if you can find the above variance, you can take the positive square root of this, and you can find the value of this. If you come here, as I said at this stage, that the variance of the error terms is rarely known. Other values we can find from the sample. What values? We can find the small x square, we can find the n, we know the n, what is the number of observation, and we can also find the capital Xi square. I have given the what is capital X and what is small x. So if we are unable to find a very important parameter, that is the sigma square, that is the constant variance, we need, it is in our formula, that how we can measure this. We go for this, we obtain it from the variance of the sample residual. So this is called the sigma hat square, and the formula for this is of this, that it is equal to summation ui hat square divided by n by 2. And how to find the summation ui square? So this is equal to summation yi square, small yi. Yi mean, small yi mean yi minus y bar. And if it's square, we will take square. And similarly xi square. So if you come to know, I have just written it, one of the formula for you people, that the beta 2 hat can be estimated by this formula. We derived a formula yesterday that was also very interesting, and this is also very simple, and small x and y are showing the deviation from the mean. And this was the variance, and this is the, you can say, the standard deviation of this. This is summation ui hat square. It is just only the, you can say, this is just the positive square root of the variance. So now I want to link that what is the relationship between variance of beta. It has now institutional values. Institution we want to draw from here. What institution we want to draw here? Look at here. The variance of beta 2 hat. Now have an eye on the formula of this, that the variance of beta 2 hat is equal to sigma square it is directly proportional to the sigma square. What this means? First of all, whether we should decide that do we want that the variance of beta 1 hat should be more or less. We want that the variation in the beta 1 hat. Now these are the estimated parameter. We want if it comes from different samples, and there the variation between the parameters value should be very small. So if you see, it has a direct and proportional relationship with the sigma square, but interestingly it has inverse relationship with the denominator. You can say that this is the denominator. So what this means, it is very simple to say that the relationship is direct or indirect. What is our purpose? Without looking at the formula, what we are intuitively deriving from this, what we say that if the variation in the error term is higher, what this means, the sigma square or the variance of the error term is higher, there will be higher variance of the beta 2 hat. That is not a good thing. And on the other hand, it has indirect or inversely relationship between summation xi square. And you know xi is equal to xi minus x bar square. So what this means, this shows the variance of the x values from their mean. So what we say here, we are confirming our previous discussion that the more variation into your independent variable, the more precise the values of your betas, and the variance of beta will skews as there is variation in your independent variable. Here is something a bit conflicting thing you may notice, that here I am saying at this stage I am saying that the variation in the residual term should be very small, and if it is small, it will push the beta variance of beta to also very small, and it has indirect relationship with the xi square. Now coming to the formula of the beta 1 hat, look at there. It has a direct relationship between this. If xi squares are very high, here xi square are very small. If xi square are very high, they will push the beta 1 variance high. And if the beta 1 variance of beta 1 is very high, it means the precision is low, because we are measuring the precision by the standard error, and standard error is simply the square root of this variance. So what we want, that there should be small value of the summation xi square. Similarly, if you are, there may be some now congestion on the board. Look at here, sigma square, the relationship is same as was in the previous with the variance of beta 2 hat. So what this is, that as the variance of the error term increases, it also pushes the variance or the precision variance of the beta 1 hat higher, and the precision becomes lower. Look at this. This is very simple concept. N. The more observation, the more data, the more precision is there. Every time we talked about that many of the problems are automatically solved when you go for a large number of data. So here it is proved that the variance or the standard error has a negative relationship with the number of observation. If your data is enough large, it will reduce and it will increase the precision of your parameters. And similarly, the summation xi square, that is the deviation of each x value from its mean. This shows that if there is a large variation in your data in the independent variable, it is a very good, and the precision of your estimates increases. If we look at here, since beta 1 hat and beta 2 are estimators, these are definitely the estimators, they will not only vary from sample to sample. Now there is another interesting stat, but in given sample, they are likely to be dependent on each other. Previously we have been talking about that what is there that from sample to sample the values of the parameter changes. Now what we are saying that within the sample the values of the beta 1 hat and beta 2 are interdependent on each other. This is called the covariance of the beta 1 hat, or you can say the parameters. This dependence being measured by the covariance. If you see that the dependence of beta 1 and beta 2 is measured by the covariation. It means we are entering into the new concept, that is the covariance of the estimator. Definitely we will have to see some of the formula. Before going to the formula, I would like to talk about the degree of freedom and covariation of the estimates. What is the degree of freedom? We will be enough talking about the degree of freedom. What is the degree of freedom? This is the difference between the number of observation and the number of parameters to be estimated. Very, very simple definition here. If you look at the board or the slide, you will see that the term number of degrees of freedom means the total number of observation, that is the n. Less means the minus the number of independent constraint, or you can say the parameters or restriction put on them. What is the general rule of finding the degree of freedom? The general rule for this is that it should be equal to n minus k. N is number of observation, and you can say the k is number of parameters to be estimated. What this is, for example, if there are n is equal to 10 and we want to measure 3 parameters, the degree of freedom will be equal to n minus k equal to 7. So this is the concept of degree of freedom. Now I am going towards the covariation of the estimates. Estimates, as I previously said, differ from sample to sample. In a given sample, beta 1 and beta 2 may depend on each other. So this is the formula for this. If you look at this, the covariation between beta 1 hat and beta 2 hat is equal to minus x bar. Minus is the sign, and x bar, you know, this is the mean and variance of beta 2 hat, and this is the formula of beta 2 hat. So if we look at the here, so since what is the relationship? Since variance of beta 2 hat is positive, look at here, variance of any number is a positive number. So what the nature of the covariance between beta 1 hat and beta 2 depends on the sign of x bar. Look at here, if I write it here, this covariance of beta 1 hat, beta 2 hat is equal to minus x bar variance of beta 2 hat. So look at this, that now the total things remains on this x bar, because there is a minus sign and this is the variance of beta 2. If the sign of x bar is positive, so the link between covariation between beta 1 and beta 2 will become negative, because if this is x bar is positive, the whole this term will be negative. What will this is that at the variance of beta 1 will increase, it will push the variance of beta 2, it will decrease. So I can read it out from here. If x bar is positive, then as the formula allows, the covariance will be negative. There will be negative. And interestingly, if the x bar is negative, then the whole this term will become positive, because this will be negative multiplied by negative, it will become positive. And if the slope coefficient beta 2 is overestimated, what this means, if x bar is positive as the formula shows, the covariance will be negative. And if the slope coefficient beta 2 is overestimated, the intercept coefficient beta 1 hat will be underestimated, and you can say the vice versa. What I can say, that if the x bar is negative, you will be thinking that how the x bar can be negative. For example, if we see the temperature, temperature, it may be negative x bar in the areas where the temperature never goes beyond 0. You can say for the Antarctica. So if this is negative, it will become positive. Now the covariation has become positive. The more variance of beta 1 2 hat, the more variance of beta 1 hat. So now it's time to give you a summary of the today discussion. What is the summary of today's discussion? We completed the assumption, the covariation, and precision error. So what are the assumptions? Simply speaking, the first assumption was the model should be linear in parameter. The second assumption was that there should be x, where fixed values of x in repeated sampling. Then there was one assumption that the sum of the residual term should be equal. There was another. Now I am not going into the justification. Now we made another assumption that the variance of the residual term should be constant. That was the homostochasticity. We further went one step and we said that there should be no autocorrelation between any of the two residual error term. You can say the error terms ui and uj. We also presumed and we said that the assumption is that there is no relationship between the ui and the xi, that the independent variable and the ui are they have no correlation between these two variables. Then we said that the number of observations should be greater than the number of parameters to be estimated. Similarly, we said that there should be no multicollinearity between the variables, perfect multicollinearity between the variables. And after this, we went for the precision of the estimate. That was a very, very important concept, that we say that there from the same population we can take many samples and every researcher will come with the different values of the beta 1 and beta 2 hat. So what is the measuring rod that could tell us that which parameter is more appropriate as compared to the other ones? So there is measuring rod that is called the standard error. Standard error is nothing but it is simply the standard deviation of the parameters. So there are formulas and you can go through other formulas also. I have given some of the formulas. So what this is, we want the minimum value of the standard error. Then we studied the covariation between the beta 1 hat and beta 2 hat. This was very interesting because from sample to sample the values of the betas keeps on changing. And here we also suppose that we do not suppose, this is the reality, that within the same sample there may be some there may be dependence of the variable of the beta 1 hat on the beta 2 hat. And there was very interesting formula that the covariation between beta 1 and beta 2 is equal to minus x bar into variance of beta 2 hat. What this means, that now the total role is now lies with the x bar, because the variance of beta 2 hat will become a positive number, because the variance of any of the number is a positive number most of the time. And what we say, that if the x bar is positive, it means the whole term will become negative, and it will link the covariation between the parameters, the intercepts and the other parameter negatively. What this means, that if the variance of beta 2 it is overinflated, it will suppress the beta 1 and vice versa. But if the x bar has a negative value, x bar may have sometime the negative value, it will make the whole term is positive. And now the previous negative relationship has turned into the positive relationship. The more variation in the beta 2 hat, the more variation in the beta 1 hat. So this was the story from me for today. So thank you very much for your kind attention, and we will continue discussion from the next lecture. So thank you very much. Allah Hafiz.